Hello, welcome to a video on using R, and we're going to look at simple linear regression from scratch. And what that means is I have a playlist called General Linear Models Regression where I'm going through a bunch of the theory and we're driving equations for simple linear regression. And I wanted to show that those formulas are indeed exactly what the built-in functions produce in R. Now I'm using data from UCLA. They have a consultant group at UCLA. They have data that I'm assuming we can use because they provide links to it. They have a great tutorial for different software packages, and we're just going to use one of their data sets. So I read in the data, and I'm going to create a smaller set of that data. Wow, it seems to be taking a little bit longer to read than usual. And the data consists of lots of different variables, but we're going to limit it to these four. And I've already created this data. It's in already in D. And so what it consists of, at least the variables that we're saving, is this academic performance index, the percentage of students who get free meals, percentage of teachers with full credentials, and the number of students. So for simple linear regression, we're only going to use the number of students to predict this academic performance. And so in simple linear regression, the design matrix is a column of ones, which corresponds to beta 0, and then the x variable or predictor, which corresponds to beta 1, and then of course the y. So I'm going to take the D, the data in matrix D or data frame D, and put it in x and y, and let's look at that. So x consists of a column of ones and then our predictor variable. Y is just the y variable associated with it. Now we're going to create a simple linear regression model, and that's what the LM stands for, linear models. And we're just going to predict the academic performance based on enrollment. We're going to use the original data D, and we're going to plot it. But then from this point forward, we're going to drive everything from scratch, and I'll show you what that means in a second. So here are the data. Here's enrollment, and here's the academic performance index. And it does look like smaller schools tend to have a little bit better academic performance. So in here, so this PV2 stands for previous video, and it's number 2 in my playlist of general linear models regression. And so the formulas in that video are what are used to derive these estimates. And so the least squares estimate for beta 1 is the sum of y times x minus the mean of x divided by this SXX, which is x minus the mean squared, and then summed. And so that's what we do. And I must say that this is definitely not the most efficient way to do it. You should always use the built-in functions, but I'm showing you that they're the same. So the least squares estimate for beta 0 is the mean of y minus the least squares estimate for beta 1 times the mean of x. And now let's look to see if that's the true. So remember, SLR is the results from our linear regression model above, and coefficient is a way to just grab out these beta 0 and beta 1. And then I'm going to use beta 0, or just print beta 0 and beta 1 to show you that they're same. So 744, all the decimals are same, as they should be, because that's the way you derive them. Now let's look at an estimate for the error variance. So this is an estimate of sigma squared. Now our fit is beta 0 times x times beta 1. So that's our fitted model. And then the error variance it's the fluctuation from our data to the fitted model, and then summed and squared and divided by this least n minus k plus 1. So let's print that. The degrees of freedom, of course, are this. It's number of rows in x, which is n, the number of columns, which is k plus 1, so it should be 2. And let's do this. So the summary of our model produces this, And the residual standard error is we're trying to grab that right there. So if we take the square root of our variance estimate, it should produce that. And it does, 135. Right? Now, degrees of freedom of 398 is 398. Now this one, we're going to find estimates for the variance of beta 0 and beta 1. And this is in PV3, previous video 3. And the reason we did this one first is we needed the estimate for the error variance, which plays a part in the estimates for the variance of beta 0 and beta 1. So here, and I'm just going to defer you back to this video, and it's essentially sigma squared, or the estimate of sigma squared divided by SXX. And just to move along, and then so that's for beta 1, and then beta 0 is this. And just to show you that they're equal is, see these right here, this is the estimates for the beta, and these are the standard errors associated with that. So it's really the square root of the variances of those. So let's look at one of them. So it's 15,93308, so it's exactly the same. And the second one, oop, it went off the screen, so let's go up a little bit here. It's the same, 02985, 02985. Now, for the sums of squares, we have total, regression, and residual. So let's plot those, and this is in previous video 7 in the playlist and number 9 in the playlist. So let's look at the ANOVA model. So that's what ANOVA from our SLR results. So we have the sum of squares due to enrollment, so that's the regression, and sum of squares due to residuals, and that's this. And so, and also the sum of these would be total. So that's what this piece does. So we want the ANOVA for the SLR model, only the sum component, which are these two, and then let's add them. And so if you take these two right here, it adds to this, and I want to check it against these. So here's the total, which equals the total from the canned package. Here is the residual, which equals the residual, and this is the sum of squares regression, which is associated with that. So now let's look at the global F test, which is PV10, and the degrees of freedom for regression is the number of regressors. Now the number of columns, we get beta 0 through beta, beta, it's 2, so it's beta 0 and beta 1, but we only have one regressor, so I subtract one from it. Residuals that's the n minus k plus 1. So the MS regression is a sum of squares regression divided by the degrees of freedom regression. The mean square residual is just the estimate for the residual variance. And now let's compare those. So the ANOVA table, and what we want to see is if this mean square regression, is the same as this, and it is. The residual is the same. Let's look at this F test statistic, which is the mean square regression over the mean square error. It's 44.8. Yep, it's the same. Now let's look at the p-value, which is you take that test statistic and find the area to the right of it, and it's 73389, to the minus 11, so it's the same. Now confidence estimates for the confidence interval beta 0 and beta 1. Now the canned package tells us it's this, so that's the confidence interval function, and here this is for the intercept, so beta 0, and this is beta 1. So let's see what we get here. So using the formula, it's beta 0 minus t sub alpha over 2 divided by the square root associated with the mean square error, and then this Yeah, so this is it, and you can I'll refer you back to the video formulas for PV12, and notice that they're the same. So 712, 92, 775, oh, minus 25, minus 14. Now here are estimates for the t-test and the p-value. So in the summary, we get this summary, and we get estimates of standard error and these t-values, which is essentially the estimate divided by the standard error, and that's what we get. And then this is the area in the tail. So if we look at the beta 0 divided by its standard error, 4671, 4671. So let's do it for beta 1, minus 6.69. It's the same. Now if we look at the p-values, now notice the second one is 100% the same, and really this one is so small that when you're so close to zero, it's kind of hard to have significant digits that are the same. So let's look at the coefficient of determination. In the standard output, it is right here, multiple squared there. It's 10, 12. So it's the sum of squares regression divided by sum of squares total, and we get the same thing. Now let's look at a prediction interval, and we have to predict for a specific value. So I'm going to predict at x0 of 1,000, and I don't know why I picked 1,000, just picked it. And then using the formula from PV14 and PV16, this is the formula for the confidence interval. So it's the variance for the confidence interval and variance for the prediction interval. And then this next is, I call it plus minus for the confidence interval. So this is the t divided by alpha over 2 degrees of freedom, and then the square root of this variance for the confidence interval. And then we do the plus minus for the prediction interval, and then plus minus for the working hoteling value. So now the function, the built-in function in R is called predict. So we use our SLO model, and we have a data frame, just one value, which is 1,000, and we want a prediction interval. And notice, so this is the built-in function on top, and then these are just using the formulas from the videos. Now the confidence interval is, we use predict2 as a general built-in function, but the type of interval we want confidence interval. And then let's look at that and notice, and I went and did the working hoteling too. So notice this is a confidence interval, and those are all the same. And the working hoteling gives sort of a guaranteed confidence interval for any x value that we pick, and of course it's a little bit wider than just the regular confidence interval. Now I want to plot these confidence bands. In the videos we drew these pretty little bands, and if you use predict without new data, then it uses the fitted model or the data or the x's in our original model, and it creates that band for all of them. And so we're going to store that in confidence band and prediction band. Now when the warning, it tells you that when you're predicting, it's actually for future responses, not on the current data. So it's a little subtlety there. Now when we plot this, we have to sort of order it, because if the x's are not in order, then it creates this jagged array, line system, which is pretty confusing. So what I want to do is order the x's, or at least know the order of the x's. So when I plot, then the lines look nice. And I'm just going to go ahead and plot all of them so we can look at them all at one spot. So this is our data from before. The black line is the regression line, simple linear regression line. The blue are the confidence intervals. So remember, for a specific value, say 1,000, we want to know what the average y is, and that's what this blue lines will tell us. We think the average will be in here, and I'm 95% confident. Now the red is a prediction interval for a particular value. And so to ensure that we get, the next value is between 2 point estimates, has to be wider, right? Because the average, if you take it big enough, it's going to be around that fitted value. But a particular point, there's a larger variance associated with it. And so that's why these prediction intervals are wider. Okay, well, that's all I have for this video. I'm going to try to sprinkle in some more using R videos into my playlist because I think it's always helpful to have real concrete examples. Well, I hope you enjoyed this. I sure did. Please subscribe so you don't miss the next one. Thanks a lot, and see you later.